So I'm Sean Parent. It's good to be here finally, 3 years delayed. I had my flight and everything booked when the pandemic hit and Phil got shut down. Since that time, I've actually restarted a group inside of Adobe, which is Adobe's Software Technology Lab, which is great. I've been doing products at Adobe for about the last 10 years. And before that, I ran the Software Technology Lab for 8 years with Alexander Stepanoff and Paul McJones and Matt Marcus and Foster Brereton. And now I've got another great team. I've got David Sankel and Dave Abrahams and Nick DeMarco. So it's really great to be back in this role. And our charter this time around is to improve software development practices. And we used to have it at Adobe as a clause there, and now it's just industry-wide. So my entire team is available to come and talk at conferences, so invite us. And we're trying to help the entire industry this time around. So why are we talking about safety, right? Why is this a theme that keeps coming up? I don't know how many people have been tracking the news as to what's going on. This is a report from 2022 from the NSA. The title there, it's a little small to probably read, but it's Software Memory Safety is the title of this paper. And it explicitly calls out C and C++ as memory unsafe languages. It has stats like this: 70% of vulnerabilities were due to memory safety issues. NSA recommends using a memory-safe language when possible. And this isn't just targeted at, like, if you're writing software for the military or that's going to be used by the government. This is a recommendation industry-wide. This was followed on by this report from Consumer Reports. This came out in January 2022. The Future of Memory Safety. It's an interesting title coming out of Consumer Reports. And here they call out memory unsafety as representing the majority of high severity security vulnerabilities, but also stability issues. So now they're shifting the focus a little bit on safety from being a security problem to being just a product quality problem. This gets followed up by the National Cybersecurity Strategy, which was published by the White House. This extends the notion of memory safety to Western democracy. Okay, so the hyperbole is getting a little out of control here. Inside of this report, they have 3 pillars of recommendations that they want to use to shape market forces to drive security. So strategic objective number 1 is hold the stewards of our data accountable, right? Which is a little bit of a shift. A lot of industries have gotten a free pass. If your systems are hacked, it's like, well, it was the hackers who were the criminals and we're just the victims. And there's been no strong government penalties. So this is an explicit shift. Shift in liability for insecure software products and services. This now extends down to the consumer level. So if your system is crashing or if your system gets hacked and is violated, it's no longer your fault for not securing your system, but it's the software vendor's fault. Strategic objective 3.5, leverage the federal procurement to improve accountability. So if you're a business that sells into the government, Adobe is a business that sells into the government, this might already be impacting you. So at Adobe now, several government agencies are requiring what's called a software bill of materials, which is an SBOM. And it's basically a list that you have to supply before you can sell to the government of all of the components that go into building your software, all of the third-party dependencies that you have, all of the tooling that you're using. And then they're going to look that up against known vulnerabilities and come back and say, say, hey, there's a known vulnerability in this component that you're using. Either you have to upgrade that component, remove that component, or file a big report with us about how you're mitigating that vulnerability. Okay? And this isn't just the US that's getting hit by this. In September 2022, the EU laid out a similar strategy in their Cyber Resilience Act. Okay? And it has this wording, which is a little bit difficult to parse, but basically it says if you're going to sell a digital good, a component or a piece of software, computer system, Internet of Things device, whatever it is, if it's got a digital component and you're selling it into the EU marketplace, then you're responsible to uphold some basic level of security and quality for your product. Which brings us to the question, what is memory safety? You would think all of these government reports, they would have a clear definition of memory safety. Well, of all the reports I just listed there, there's only one report that actually gives any definition of what memory safety is. And that's the initial NSA report, and this is all it has to say about it. Okay? So that's a bit of a problem. Now, to be in all fairness to the NSA, they do go on to give a bunch of examples. They talk about double-free and uninitialized variables and data races, but they're just listed as example, this set of things. Right? So what is memory safety? Right? We need to figure this out. Well, you go look on the web, you get a lot of definitions. Here we go. Memory safety is the state of being protected from various software bugs and security vulnerabilities when dealing with memory access, such as buffer overflows and dangling pointers. Okay. We define a program as being fully memory safe if it satisfies the following criteria. It never reads uninitialized memory, performs no illegal operations on the heap, no invalid double frees, and does not access freed memory, no dangling pointer errors. Okay, overwriting the stack is fine, apparently. Just stay off the heap. Memory safety is the property of a program where memory pointers used always point to valid memory. Weak. Memory safety is a term used by software and security engineers to describe applications that access the operating system's memory in a way that doesn't cause errors. Okay. Somebody said memory safety is about race conditions, concurrent reads, and writes to shared memory. Or it's about unwanted aliasing, as opposed to desirable aliasing, when the same memory location is allocated and modified twice for unrelated purposes. So what is memory safety? Right? I mean, if we're going to legislate it, you would think we would have a clear definition. So let's back up a little bit here. It turns out that the terms safety properties and safety are actually well defined in computer science, but you have to go back a ways. The safety of a program is a set of safety properties that cannot happen given valid input. That's what the definition of safety is. Where does this come from? So it comes from Leslie Lambert in a 1974 paper. And this is actually a good definition. The context of this paper is talking about proving the correctness of multi-process programs. So he's talking about concurrent software. How do you prove the correctness of concurrent software? But the definitions here are an extension of the definitions of software correctness for single process systems. And as such, the same rules apply if you go back from multi-process to a single process system. So he talks about to prove the correctness of a program, one must prove two essentially different types of properties about it, which we call safety and liveness properties. A safety property is one which states that something will not happen. A liveness property is one which states that something must happen. Okay. So, as I said before, safety properties are a generalization of what's known as partial correctness in computer science. And if you think about proving loops being correct, they're very much an extension of that. So a safety property is akin to an invariant that must hold on every iteration of your loop, and a liveness property talking about will your loop terminate. But they're extensions of that basic model from just loops to the execution of your entire program, even in a concurrent system. So, if some execution of an operation does not satisfy a safety property, then the defining bad thing occurs at some point in that operation. Okay, so if we think about that, that puts a bound on what we call a safety property, right? What we're trying to say is when a bad thing happens, it happens at some specific point in time, which is a little different than a liveness property, which might be talking about when your program is going to terminate. That doesn't happen at some specific point in time. Safety properties are irremediable. What does that mean? It means that once the bad thing has happened, you can't take it back. Okay? The once you wrote off a null pointer, you're toast. You're done, right? So if the execution continues, even with subsequent operations, it doesn't matter, right? That bad thing still happened. And safety properties compose. This is a very powerful notion. Right? What do we mean by that? We mean if every operation within your system satisfies a safety property, then it doesn't matter how you combine them. The system as a whole satisfies the safety property. Okay? It's that last point that makes these a very powerful tool. So let's give an example. Our self-driving car. What we want as a safety property is that the car cannot drive off the road. Right? So a safe operation doesn't allow the car to go off the road. A little asterisk here, which we'll come back to. So if all operations can be shown to satisfy the safety property, then the condition prevented by the property cannot occur. Right? So if there's no operation in our self-driving car that would allow the car to drive off the road, then the car can't drive off the road. The asterisk there is, in this context, we're assuming the preconditions of these operations are not violated, which is when we're talking about safety properties in the context of Leslie Lampert's safety properties, we're talking about things in a system that we're trying to prove correct. So the assumption is that all of the contracts already hold. So an example of our liveness property for a self-driving car. The car will eventually reach its destination. Right? That's a liveness property. So this may be achieved by a series of stepwise refinements. Right? The car gets closer and closer and closer to its destination, and eventually we can prove a termination. In fact, if you're looking at how do you prove loop correctness, a loop termination within a program or recursion termination, you always have to find some mapping of your loop or your recursion onto natural numbers and then show that that natural number is decreasing at every step until it terminates. It's the same thing with a liveness property. So the safety of a program, so now let's switch this from, we were talking about software correctness in a very general context. But now let's shift our focus a little bit, because when we were talking before, when we were looking at the reports, we were talking about memory safety in the context of programming languages. So now let's shift from talking about correctness of our system to what it means for a programming language to be safe. Right. So the safety of a programming language is a set of safety properties guaranteed for any expressible program. Right. So when we're talking about a programming system that provides memory safety, maybe we're talking about JavaScript provides some level of memory safety, right? And you can say, oh, well, there's no way within JavaScript for you to follow a reference to an object and have the object not be there, right? You can't access it. Maybe it's null, in which case you'll get an error out, but there's no way to just write off into the heap, right? So that inability to access just raw memory inside of JavaScript is a safety property of JavaScript. So every program that can be written in the language or a safe subset of the language, because a lot of languages give you a backdoor to kind of step out of safety, satisfies the safety properties of the language. So there are three primary ways that a language can achieve a safety property. One is by limiting the expressibility, right? Just don't let you say the bad thing, okay? An example of this, Haskell doesn't let you describe mutation, okay? So you can't get a race condition by definition in Haskell. It's just not expressible within the language. Another thing that a language can do is it can do runtime validation. It can check, usually just before the bad thing happens, and then either return an error or terminate your process to prevent that bad thing from happening. Right? So as an example, in the Swift language, if you do integer overflow, it will trap. It will not continue execution from that point. You can also define away the bad thing, right? Define the behavior of some operation that might otherwise be unsafe. So indexing an array out of bounds inside of JavaScript will return a value that's called undefined, right? As opposed to just letting you access random memory off the end of your array. Okay. Now there's a caveat that goes with that last part, and that's that now you're going to allow the program to continue to execute, right, with potentially invalid values, which might cause the damage of your defect to spread. And we'll talk a little bit more about that in a moment. So here is how most people define a memory-safe language. They say the language has no operations that access memory which is not allocated, has not been initialized, or has been released. Do people think that that's good? Is that a good definition? Maybe. Well, what we didn't say here, we're not preventing our car from driving on the wrong side of the road. We're keeping it on the road, but we're not preventing it from driving on the wrong side of the road. What do I mean by that? Let's take a little example here in C++. I've got this piece of code. It's got one function which can set an element of an array, and it just blasts that element to 42. I've got my array, which has 1, 2, 3, some what variable, which is 0. I set element. I want to blast the number 3 in my array to be 42, but I've got a bug. Everybody see what the bug is? Right? C++, we start counting at 0. So we're blasting 1 off the end. So when I print out what do I get? I get 42. Okay? Now, did I access memory that wasn't allocated? No. Did I access memory that wasn't initialized? No. Did I access memory after it had been freed or released? No. I followed all of my rules on memory safety, okay? And in fact, because this data is so close, your address sanitizer may or may not even catch this. Okay. So we haven't really defined what our problem is. When I work at Adobe, I monitor, we've got a Slack guild, C++ guild, and I monitor the questions there. And a lot of times the questions are, how do I do blank? Okay, and what's the first thing that I usually respond with? What are you trying to do? Okay, okay. People tend to jump to, I'm just trying to wire up this piece of code and the compiler's giving me an error, and not step back and say, wait, what's the problem you're actually trying to solve here? So what's the problem that the security industry is actually trying to solve by going after memory safety? Right? Because they're trying to solve a different problem than what a lot of the languages and the software industry are trying to solve, right? And unless they come up with clear definitions about their stuff, we hit this problem of well, it's okay to just let our car drive on the wrong side of the road, right? We can solve this problem with sandboxing, right? Okay, we can just put a tight box around the whole thing and solve all the security issues. It sounds reasonable. But here's the actual problem. A secure system is a system where the resources are used and accessed as intended under all circumstances. It's just a textbook definition of what a secure system is. So any defect can cause resources to be accessed in unintended ways. So language safety can aid security by making defects harder to write and easier to see when you do write them, and containing the damage due to a defect. And it's the containing the damage there that's actually the most important part. So a key property of a secure system is a property known as a non-interference property. Right? What does that mean? Well, a non-interference property holds if and only if any sequence of low inputs. What do we mean by a low input? We mean if you're a user of a system and you don't have particular access or privileges in that, then your input is low input. Okay. We'll produce the same low inputs regardless of what the high inputs are, which means the system is running at a higher privilege level, so it's got high inputs. Okay. And so no matter what you do, you kind of can't interfere with that other side. So that's what this property is getting at. Now, the tough part is that the non-interference property is neither a safety or a liveness property. It's something known as a hyperproperty. Okay. And that's a challenge. That means within our programming language, we can't just make a simple rule that says you can't do some bad thing and solve for the non-interference property. The reason why the security industry is going after memory safety is because memory safety, the safety properties around memory, assist with the non-interference property by containing the damage due to a defect. Okay? So that's what they're going after. So what is a memory safe language in this context? Well, there's this paper. This came out in 2018, fairly heavily cited. I think it's the best definition of memory safety to date, but it doesn't define memory safety in terms of safety properties. So that's the info on it. So this paper defines memory safety in terms of something called a frame rule. So what's a frame rule? Well, in English, it says a verified program can only affect a well-defined portion of the state, leaving all other memory regions untouched. Okay? So it's very much focused around this idea of how do we contain the damage? How do we prevent information leaks from one part of a system to another part of the system? It's inspired by separation logic and the ideas behind local reasoning. And the frame rule is proven in this paper to actually satisfy the non-interference property. So the frame rule relates to something John McCall coined as the law of exclusivity from Swift. It also connects directly to the borrow checker in Rust. Okay? It is satisfied in some sense by all functional programming languages. If you eliminate mutation, you prevent one part of a system from directly affecting another part of the system. A big caveat there, which I'll mention in a bit. So how do we take the frame rule and apply that to a programming language? Well, I spent some time with Dimi Ricardon, who's the designer of the Val language. She's actually an expert in the frame rule, and we came up with this phrasing, right? A verified program can only affect a well-defined, we want to restate that. An operation can only access and affect objects defined by the operations interface with all other objects unaffected, right? And the law of exclusivity from Swift follows from that statement. In fact, the law of exclusivity is actually a slightly weaker version of that statement. So where does all of this leave C++? Well, as soon as you have shared mutable references, that makes memory safety only possible with great discipline, right? It is hard to achieve. The language is not going to help you. Sanitizers can help by catching your mistakes early, but sanitizers have a lot of limitations, and typically you can't run them in production because the performance is too awful. So if you're using sanitizers, I say you have to be also using fuzzing, right? Because you want to be making sure that if somebody is trying to explicitly attack and exploit your system, that you're preventing that. So you need to be able to fuzz all of your input that could come from an untrusted source feeding into your system with your sanitizer to try to catch as many mistakes as you can. And the sad reality is no safety properties hold in the presence of undefined behavior. Right? In fact, that last statement is actually worse, which is no properties hold in the presence of undefined behavior. That puts C++ in a difficult position, and C as well, right? If you look at the C++ spec, I think last time I did a search on it, the term undefined behavior appeared something over 300 times. Every call within the standard library, if you don't satisfy the preconditions, it's undefined behavior. So this is all well and good. So years ago, Alex had this statement, made this statement to me. I was talking about, I had spent a fair amount of my career from the time I first joined Apple, so like 88, I guess, 87, 88, that time frame, up through a good section of my career at Adobe, trying to understand how you could prevent software from failing. And I was talking with Alex about this, and he said, yeah, understanding why software fails is important, but the real challenge is actually understanding why software works. Why does this statement resonate? A lot of times when we're chasing safety properties and trying to prevent bad things from happening, we lose sight of the fact that our ultimate goal is to assist developers in writing correct software. That's the reason why we have safety properties to begin with. The origin of safety properties is around how do you prove your software to be correct, okay? And so a lot of times I see this in the C++ community and in the C++ standard. You see, well, why don't we just take that undefined behavior and define what the result will be? And remember earlier I said sometimes if you just define what the result is in a nonsensical case, right? If you say, oh, I'm just going to say integer overflow for signed integers is just going to work wrapping modulo 2. Well, almost nobody ever means that they want modulo 2 arithmetic when they overflow their integers. That's probably a bug. And now you just allowed that bug to escape and spread throughout your system. And you just violated the non-interference property. And now at some point, some security researcher is going to come and say, hey, this bug in your code caused this exploit, right? So you have to be careful. The goal here when you're defining this stuff is how do you get to correct software, not just how do you eliminate undefined behavior. The other thing I want to tell you is that all of this safety stuff, all of this non-interference stuff, is in some sense an illusion. And what do I mean by that? I mean that if your system, if your language is Turing complete, okay, then inside of that, you can build an unsafe system. No matter how safe your Turing complete system is, inside of it, you can build an unsafe system. Inside of JavaScript, you can build a C machine and execute C and C++ code. That's what asm.js is, and that's where WASM came from. Okay? Now, conversely, almost every safe system is built on top of an unsafe system. Okay? So this notion of safety applies at a given abstraction level. And where that abstraction level is depends on how you define what an operation is. And this is true of software correctness too, right? You can talk about the correctness of the program that you write with respect to, say, the C++ language spec. Is this correct C++ code? And that's a different thing than saying, is this a correct code for high-speed trading? Okay, does it satisfy a different spec? So both when you're talking about safety and when you're talking about correctness, you're talking about it at a given abstraction level. Why is this important? Because as soon as I give a developer a safe tool, if the developer doesn't understand what my goals are, that I'm trying to achieve a non-interference pattern, and a developer has a particular way that they're trying to solve a problem, they will, surprisingly, create an unsafe system inside of my safe system because that's how they're thinking about the problem. Anytime you see somebody doing like recycling objects inside of JavaScript, right, for performance, they're trying to, you construct an object, instead of just letting the garbage collector handle it, you stick it on a free list and you recycle that object. Okay? You're violating the intent around memory safety. You're opening up the possibility of having interference across sections of your application if you don't correctly reinitialize those objects that you're recycling. You're letting information leak from one part of your system to another. In fact, anytime you create an extrinsic relationship, which we define to be a relationship that's not a whole part relationship, so a relationship between objects within your system that's not under a strict whole part value semantic whole. So whether or not that relationship is one that's going up to some parent object or going across to some sibling object, or you're just building a graph of objects within your system. Anytime you have extrinsic relationships, in some ways, you're violating this notion of non-interference. Okay? So even within a memory safe system, as soon as I say, oh, I have this memory safe system and I'm going to keep an index around to my object in the array and reference things via my index. Well, an index is really not fundamentally different from a pointer. All a pointer is an index into memory, right? So as soon as I start to establish those additional relationships and build those networks, in essence, I'm building an unsafe system inside of my safe system. And this is one reason why I mentioned earlier that I was going to loop back to this idea of functional programming satisfies all of the non-interference properties and all the safety guarantees by disallowing mutation. The problem with it is that by disallowing mutation, I don't have a way to express whole part relationships other than using extrinsic relationships. Which means that inside of functional systems, what you see over and over and over again is people reinventing unsafe systems to pretend that they have mutation, even though they don't have mutation, to make things work as if they had mutation, with no clear demarcation between the whole and the parts, okay? Which means no clear demarcation with where interference can happen across the application. So the two languages that I think do this better are Rust. Rust at least makes that mutation explicit. It doesn't represent things as whole part relationships. It's still a reference semantic relationship language. There's a fairly trivial transformation between Rust and pure functional programming. But it makes that mutation explicit, which at least allows you to talk about that. The other right now is Swift. Now, half of Swift comes out of Objective-C, and that's all reference semantic stuff. But half of Swift is following John McCall's law of exclusivity and is strong value semantics and whole part relationships. And where the language val that my team is working on comes from is taking that other half of Swift and saying, how far can we push this? And we think that that's got a lot of potential because representing things in terms of whole part relationships we find easier for developers to grok, and it means that you can write safe code without the non-interference property without having to do so much explicit tracking of lifetimes and ownerships, of which you have to in Rust. So it provides all the same guarantees as Rust. It just happens automatically. So safety can always be circumvented, and often is. So safety itself is a tool. It's a tool that we use for local reasoning, right? When we're looking at a piece of code and we're trying to determine whether or not this piece of code is correct, we want to be looking at what are the safety properties that this piece of code upholds, and how do I know that? One of my canonical examples is a mutex. If you call a mutex and you satisfy all the preconditions of the mutex, so you're not going to crash, right? And you're calling lock on it. What guarantees do you have? Do you guarantee that you're not going to deadlock if you lock a mutex, right? None of those guarantees are provided locally. All of those are extrinsic guarantees. To understand whether or not you're using a mutex correctly, you have to understand some subsection of your system, at least some subsection of your system, depending on what a mess your system is. Maybe you have to understand the system as a whole. Okay? You have to keep all of that in your head. So when you're looking at writing your own constructs, one of my talks, I say, I have these goals or rubrics, things like no raw loops. I think most people have heard no raw synchronization primitives. Why do we want no raw synchronization primitives? Because they break local reasoning. Okay. So why do we want no raw loops? Because they make local reasoning difficult, because loops are difficult to reason about. So when you're writing your own code, you want to be looking at what are the safety properties that I want to uphold? What are the safety properties that are important for my project? And how do I uphold them in my code? So can C++ be memory safe? Well, not without significant changes. And it will require an explicit safe subset. And there's a necessary shift at the abstraction level, right? Why do I say necessary? Because I don't think if you just said, I'm going to go and make all of the operations in C++ safe, first you couldn't, right? Think about things like thread safety. How are you going to do that when you have shared references going everywhere? Within the current confines of the language, I just don't think there's any way to do it by just subsetting and cutting off parts of the language. If you manage to pull something off, it would be very inefficient. So where does C++ go? Well, I don't know. I don't have the answer for that. I'm putting a hard right turn, though, in my talk here. I've decided that all opening keynotes should end with a foreword. So hopefully this is going to be something that will spur a conversation for the rest of the conference and get you guys talking. So quite a while ago, what year was it? 2007, I gave a tech talk at Google that was titled A Possible Future of Software Development. It's still online. It's a very old talk at this point. A little embarrassing to watch younger me give a talk. But it basically boiled down to two key points. One is, I think, as an industry, we need an extensive library of proven generic components, okay, from which we can assemble our software. This is not just my dream. I actually stole this from Alex Stepanoff. When I first met Alex, he came and gave a talk at Adobe in 2002. That talk's also available online. And this was very much his dream. These days, he'll give you a long explanation as to why he thinks that will never happen. I still hold out. So, and then, this is my addition. I think we need a small number of non-Turing complete declarative, what I call forms, for assembling the generic components. Okay, so what's a declarative form? Well, a good example would be grammars, right? Grammars are a way that you describe a parser. They're a declarative form of a parser. Just by spelling out the grammar, you completely define how a parser works. Layout systems also fall into declarative forms. I've spent a lot of working on something called, or a lot of time working on something called property models, which are a declarative form to let you describe relationships between discrete properties. And basically, I think you need a small number of these forms for assembling those generic components to build your system, right? So we shouldn't actually be writing imperatively the code that we write. We should be declaring the code that we write on top of this generic library. And at one point, I spent some time with Jaakko Järve, who worked with Bjarne at Texas A&M, and now he's a professor in Oslo, I think? Finland. Turku, Finland. In any case, Jaakko spent his sabbatical at Adobe, and we went through, and we conjectured that you probably need about 6 declarative forms to fully describe Photoshop. And if you had those forms, it would be about 2 orders of magnitude less code. And we kind of worked up some examples as to how that would look. So I think if we could actually get there, it would be industry changing. Now, I've been saying this since 2007, so take that with a grain of salt. But since I gave that talk, before I walk you through this slide, 2 fundamental things have changed. The first is the amount of computational resources that we have at our disposal has gone up astronomically. Okay, we can solve problems now that the 2007 me just dreamed about. The other thing that's happened relatively recently has been large language models. Okay, and I'm going to show you why I think that large language models are important. This piece of code here is written in a language called Daphne. How many people here have ever heard of Daphne? 1 or 2. Who's ever played with Daphne? Nobody. Okay. I'm kind of surprised. Daphne is at version 4 right now. It's a semi-mature-ish little language. It came out of Microsoft Research. It is a language within which you can incrementally prove your code while you're writing it, right? So if you think about C++ contracts, in the same vein, we have ensures here. That's a precondition. Or I'm sorry, ensures is a postcondition. Requires would be a precondition. We have loop invariants to try to prove out the loop. Now, this piece of code is a fairly trivial piece of code. It's doing a bad job of reversing a sequence here. A sequence in Daphne is the moral equivalent to a view inside of C++, so it's not actually the elements, it's just a projection onto the elements. So we're trying to reverse the projection, not reverse all of the items in the projection. Daphne itself compiles down to, it's a transpiler, so it compiles down to a bunch of different languages. One of those languages is actually C++ now. So you can use Daphne to develop and prove your C++ code, which is kind of fun. That's one of the reasons why I'm interested in Daphne, playing with it. So I was working on this piece of code, and I hit this problem. So I'm trying to reverse the sequence, and I've got, get a pointer here. I don't have a pointer. I've got my post conditions ensures, and what I'm trying to do is I'm trying to write a post condition that says that this sequence is reversed. So I'm saying for all elements I, such that I is between 0 and the length of A, that implies that my result, which is R sub I is equal to my original sequence, A sub length of A minus I minus 1, right? So the result of this thing is a reverse of the original, is what that's saying. So inside of my loop, I'm basically echoing that as a loop invariant, so that each time through the loop, I'm saying that the piece of the sequence that I've processed so far in the loop is a reverse of the other part of the corresponding other part of the sequence of the source. So that's my loop invariant. But I can't prove, I had to comment out that ensures up on top, I can't prove it because I'm getting this error. This loop invariant might not be maintained by the loop. It is maintained by the loop, but Daphne, which has a half a dozen algebraic solvers in it, can't prove it. It can't get there from here, okay? So usually when this happens, you have to tell Daphne like one more invariant. I need to tell it more about this loop so that it can prove that statement, which will then prove my post condition, and I will have a formal proof for this piece of code. I just can't get there. And literally working on this piece of code, I was stuck. I'm like, okay, very frustrating. And this is true if you've ever dealt with any formal method system, right? Trying to prove things in a formal method system is a challenge. Now, by just commenting that out, both of those invariants, I can make the code compile and run, which is kind of cool in Daphne. You can incrementally get into it, so you can actually see, does this run? Does it do what I expect? You don't have to prove everything up front. So in desperation, I went to Bing Chat, and I said, how can I strengthen the loop invariant in the following Daphne code to convince Daphne that the loop invariant holds? And then I gave it the code that you just saw. And I did not expect any kind of sensible answer. I really didn't. Here's the answer I got. You can add an invariant that ensures that the elements of remainder are the same as the elements of A that have not yet been added to R. Here's an example. And then it gave me the invariant. So this invariant states that for all, now it's explaining it to me. This invariant states that for all indices I in the range 0 to the length of remainder, the ith element of remainder is equal to the I plus length of rth element of A. This ensures that the elements of remainder are exactly the elements of A that have not yet been added to R. Okay? That's absolutely correct. I put in that invariant, it completes my proof. I now have proven post conditions. That's nuts. Okay. My conjecture as to why this works, because I've tried a bunch of these AI systems with C++ code, and they almost always get it wrong. I've actually had very good luck with AI systems with Daphne. And my conjecture is because the only things that that these large language models, that these LLMs, have seen of Daphne code is correct Daphne code. They haven't seen all the bad examples to learn from them, right? Because if you're going to put up Daphne code, it's going to have a proof that works almost always. Okay? So I'm adding to my new possible future here, built with AI-assisted verification. Right? And I think we're kind of on the cusp where this is feasible. If I were to sum up what my personal thesis is, my career thesis, it would be that all professional developers can routinely write correct and efficient code. Right? As a thesis, that's, I believe, a statement of fact. I believe that that's true today. My career goal is to change the word can to do. Right? I want all professional developers to routinely write correct and efficient code. And I think we're slowly putting the pieces together to get us there. And that's become my thesis for the team that I'm running. Right? How do we get from can to do? How do we get so that every developer, when they sit down, they routinely write code that is correct, and I mean correct as in provably correct, and efficient. And when I say efficient, I mean there is no other way to represent that piece of code that would be faster. Right? So those are very absolute terms. So as a closing, despite all the hyperbole, memory safety actually is important. It's a problem in this industry that software doesn't just work, right? The number of times I see a piece of defective software or have a software failure, I count multiple times a day, right? And that's not software I'm developing, that's just software I'm using as a customer. I view that as being unacceptable. We can use safety properties so that our code doesn't do bad things. And we can use the frame rule and this idea of non-interference to try to promote security and local reasoning, right? This helps you as a developer as well as helping the security industry. The security industry, a lot of people are like, well, they're just trying to protect systems and I'm not worried about the safety of my system, right? Who cares if somebody exploits my system? I hear that all the time. Your customers actually do care. But at the end of the day, we have the same goal. Our goal is how do we write correct software, right? That's what the security industry wants. They want correct software because that's the only thing that solves all the security issues is if there's no bugs in the software. And the only thing that makes all of your customers happy, assuming you're a professional developer and you have customers, is that you have no bugs in your software. So don't lose sight that correctness is the goal, right? Because the safest car is the car that doesn't go anywhere. So that's the end of my talk.